Hello there, and welcome to this quiet corner where curiosity meets the vastness of deep time, and wonder is allowed to unfold without hurry. Tonight, we're stepping back through an almost unimaginable span of years, back to when Earth wore a completely different face, when the very air hummed with life forms so alien they might as well have been from another planet entirely. Here's something that might stop you in your tracks. For every single year that humans have walked this earth, dinosaurs ruled it for over 30,000 years. Think about that for a moment. Every birthday you've celebrated, every historical event you've learned about, every story passed down through generations. Multiply that entire human timeline by 30,000, and you're only beginning to glimpse the reign of the dinosaurs. This is the Age of Dinosaurs, a chapter of our planet's story so vast and so strange that even now, we're still uncovering its secrets, buried in stone. Before we begin this journey, I'd love to know where you are right now as you listen. Perhaps it's late at night, and you're looking for something to carry you gently into sleep. Maybe you're curious about the deep past, drawn to stories that stretch beyond the comfortable boundaries of human memory. Wherever you are, whenever this is, settle in, because we're about to walk through a world that existed for over 160 million years. A world that, in many ways, laid the foundation for everything you see around you today. If this kind of slow exploration through deep time speaks to you, if you find yourself drawn to these quiet journeys through Earth's forgotten chapters, I'd be grateful if you let me know by subscribing. It helps this small voice reach other curious minds scattered across the globe. No pressure, of course, just an invitation to join a community of people who believe that the past has stories worth telling, and that sometimes the most profound discoveries happen when we simply take the time to listen. So let's begin. Not with the thunderous roar of a Tyrannosaurus or the earth-shaking steps of a Brontosaurus, but with something subtler. Let's begin with the silence that came before, a silence so complete it marked the end of one world and the hesitant beginning of another. 252 million years ago, Earth experienced what scientists now call the Great Dying. It wasn't dramatic in the way we usually imagine catastrophes. There were no sudden explosions, no immediate collapses. Instead, over the course of thousands of years, life simply faded. The oceans grew still, the forests withered. 90% of all species that had ever existed vanished into the stone record, leaving behind a planet that was, for a brief moment, in geological time, profoundly quiet. It's difficult to imagine such emptiness. Today, even in our most remote wilderness areas, life fills every available niche. Bacteria thrive in boiling springs, tiny organisms flourish in the deepest ocean trenches, and somewhere, always, something is growing, hunting, reproducing, dying, and being reborn. But in the aftermath of the Great Dying, vast stretches of Earth lay barren, waiting. The cause of this extinction remains one of geology's great mysteries. Perhaps it was massive volcanic eruptions in what is now Siberia, belching ash and poison gases into the atmosphere for thousands of years. Perhaps it was a shift in ocean chemistry that stripped oxygen from the water. Perhaps it was climate change so severe that the planet's thermostat simply broke. Or perhaps it was all of these things working together in a cascade of catastrophe that no single species could survive. But here's what makes this story remarkable. Life didn't give up. In the ruins of that devastated world, something stirred. Small creatures, unremarkable by the standards of what had come before, began to venture out from whatever refuges had sheltered them through the dying time. They were mostly reptiles built for a world growing warmer and drier. They had stronger lungs than their predecessors, more efficient hearts, and bones that could support their weight as they moved away from the water that had nurtured their ancestors. These survivors found themselves inheritors of an empty earth. Ecological niches that had been filled for millions of years now stood vacant. Rivers flowed without the massive amphibians that had once ruled them. Plains stretched endlessly without the herds that had once grazed them. It was an opportunity unprecedented in the history of life, a chance to start over, to experiment, to become something entirely new. And so began the Triassic period, the first chapter in what we now call the Age of Dinosaurs. But the creatures that would eventually become dinosaurs were still small, still cautious, still learning how to live in this strange new world. They shared their landscapes with other survivors, early mammals no larger than shrews, crocodile-like archosaurs that would grow into formidable predators, and the last of the great amphibians clinging to existence in the shrinking wetlands. The Earth they inherited was unlike anything we know today. All the continents were fused into a single, massive landmass called Pangaea, surrounded by one enormous ocean. Imagine a world with no Atlantic separating America from Europe, no Pacific dividing Asia from the Americas. Instead, you could theoretically walk from what is now New York to what is now Morocco without ever seeing the sea. This supercontinent created its own weather patterns, its own extremes. The interior was a vast desert, scorching hot and bone dry, but along the coasts, where ocean breezes could reach, life found footholds and began its slow recovery. The early dinosaurs were nothing like the giants we imagine when we hear their name. The first true dinosaur fossils we've discovered, creatures like Eoraptor and Dilophosaurus, were small, swift, and built for speed rather than power. They stood perhaps 3 feet tall, ran on their hind legs, and hunted insects, small reptiles, and whatever other prey they could catch in a world, still learning how to be abundant again. But even in these humble forms, you can see the seeds of what was to come. Their hip structure was subtly different from other reptiles, allowing for a more upright stance and more efficient movement. Their breathing was more sophisticated, with air sacs that would later allow their descendants to grow to enormous sizes, while still getting enough oxygen to their tissues. Most importantly, they had already begun to experiment with different ways of life. Some early dinosaurs remained carnivorous, perfecting their hunting techniques and developing increasingly sophisticated methods of catching prey. Others began to shift toward plant eating, their teeth and digestive systems adapting to process the tough, fibrous vegetation that dominated Triassic landscapes. This dietary flexibility would prove crucial as the world continued to change around them. The Triassic world was harsh but not lifeless. Forests of conifers and cycads dotted the landscape, their needle-like leaves and waxy surfaces adaptations to the hot, dry climate. These weren't the flowering plants we know today. Those wouldn't appear for another 100 million years. Instead, the vegetation had an alien quality, dominated by plants that looked more like oversized ferns and palm trees than anything in a modern forest. In the rivers and lakes, massive amphibians still ruled. Creatures like Mastodonsaurus, with skulls over a meter long, lurked in the shallows, waiting for unwary prey. Alongside them, the phytosaurs, crocodile-like predators with nostrils positioned on top of raised bumps on their skulls, competed for the same aquatic territories. These were formidable predators, and the early dinosaurs gave them a wide berth. On land, the competition was just as fierce. The dominant predators were not dinosaurs but other archosaurs, relatives of crocodiles and birds that had evolved into forms we can barely imagine today. Some, like Postosuchus, grew to lengths of 5 meters and walked on their hind legs like massive carnivorous ostriches. Others, like Desmatosuchus, were heavily armored herbivores that looked like walking tanks. For most of the Triassic period, dinosaurs remained bit players in this drama. They were successful, certainly, and they were spreading across Pangaea, but they hadn't yet achieved the dominance that would define the later Mesozoic era. That would require another catastrophe, another mass extinction to clear away their competitors and give them their chance to inherit the Earth. As the Triassic period drew to a close, the planet began to change in fundamental ways. Pangaea, that massive supercontinent that had dominated Earth's geography for millions of years, started to crack. Deep beneath the surface, hot plumes of magma pushed upward, stretching and weakening the continental crust. What began as small fissures gradually widened into great rift valleys, and eventually these valleys would become the beginnings of new oceans. The breakup of Pangaea didn't happen overnight. It was a process that would continue for millions of years, but its effects were immediate and profound. As new seaways opened up, ocean currents that had circulated around the supercontinent for eons were disrupted. Weather patterns shifted. The great interior deserts began to shrink as moisture from the new seas penetrated deeper inland. This might sound like it should have been beneficial for life. More water, more moderate climates, more diverse habitats. And in the long run, it was. But change, even beneficial change, is rarely easy for the creatures living through it. The shifting climate put stress on established ecosystems. Food webs that had been stable for millions of years suddenly became unreliable, and then, as if the geological upheaval wasn't enough, the volcanism intensified. Massive eruptions, primarily in what is now the eastern coast of North America, began pumping enormous quantities of lava, ash and toxic gases into the atmosphere. These weren't the explosive eruptions we might think of when we picture volcanoes. Instead, they were flood basalts, vast outpourings of lava that covered thousands of square kilometers in molten rock. The gases they released changed the chemistry of the atmosphere and oceans, making life difficult for many species. The end result was another mass extinction, smaller than the Great Dying that had ended the Permian period, but significant enough to reshape the biological landscape once again. And once again, dinosaurs were among the survivors. This time, however, they didn't just survive, they thrived. As their competitors disappeared, dinosaurs rapidly diversified to fill the newly vacant ecological niches. The small, swift hunters of the early Triassic gave rise to larger, more specialized forms. Some developed into the first giant herbivores, early sauropods that would eventually become the largest land animals in Earth's history. Others perfected their predatory skills, evolving into the ancestors of the fearsome theropods that would dominate Mesozoic food chains. The stage was set for the Jurassic period, the golden age of dinosaurs, when these remarkable reptiles would truly come into their own and transform Earth into something that would have seemed like pure fantasy to any observer from our modern world. But that transformation didn't happen immediately. Evolution, for all its creativity, is patient. The dinosaurs that emerged from the Triassic extinction were still finding their footing in a world that continued to change around them. The climate was shifting from hot and dry to warm and humid. New plant communities were establishing themselves in the increasingly fragmented landscapes. And in the oceans, marine reptiles were beginning their own extraordinary evolutionary journey. As we prepare to step into the Jurassic world, imagine Earth as a planet in transition. The familiar shapes of modern continents were beginning to emerge from the wreckage of Pangaea, but slowly, almost imperceptibly. New mountains were rising along the rift zones where the continents were pulling apart. Shallow seas were flooding low-lying areas, creating vast inland waterways that would support entirely different kinds of life. And everywhere, in this world of gradual but relentless change, dinosaurs were learning to be giants. The next chapter of their story would unfold in forests more lush than any that exist today, under skies thick with humidity and filled with creatures that had never flown before. It would be a world of such abundance and diversity that we're still discovering new species from this time, still trying to understand how life could have been so magnificently, impossibly rich. The Jurassic awaits, and with it, the true flowering of the dinosaur age. When the Jurassic dawn broke over Earth 199 million years ago, it revealed a planet transformed beyond recognition. The air itself had changed, thick with moisture that rose from newly formed seas and settled into valleys where ancient deserts had once stretched endlessly. If you could have stood on one of those early Jurassic mornings, breathing that humid, oxygen-rich atmosphere, you might have felt as though you were standing in the lungs of some vast, living creature. The breakup of Pangaea had fundamentally altered Earth's climate system. Where once there had been one massive ocean circling a single supercontinent, now fingers of seawater were beginning to probe inland, creating shallow tropical seas that acted like enormous humidifiers. The temperature gradient between the equator and the poles softened, creating a world where even the Arctic regions enjoyed temperate, forest-like conditions. There were no ice caps anywhere on the planet, no frozen wastelands, no seasons as we understand them today. Instead, there were rhythms of wet and dry, of abundance and plenty. The great interior deserts of the Triassic gave way to vast river systems that meandered across continents, their waters brown with sediment from the rising mountains where the continents were pulling apart. Along these rivers, forests began to establish themselves, unlike any that exist in our modern world. These were not the flowering woodlands we might recognize today. The trees were predominantly conifers, their needle-like leaves adapted to extract maximum benefit from the carbon dioxide-rich atmosphere. But interspersed among them were stranger forms, cycads that looked like palm trees but reproduced with cones, tree ferns that could grow 50 feet tall, and ginkgos whose fan-shaped leaves carpeted the forest floor in golden drifts when the seasons turned. The understory was a wonderland of ferns, some delicate as lace, others tough and fibrous, all of them thriving in the perpetual twilight beneath the canopy. Horsetails grew in vast stands along the riverbanks, their jointed stems creating natural bamboo groves that rustled with the movement of creatures we can only imagine. And everywhere, the air hummed with the sound of insects. Though these were insects scaled to match their world, dragonflies with wingspans measured in feet rather than inches. It was into this Eden that dinosaurs stepped and began their transformation into giants. The early Jurassic marks the true beginning of their golden age, when the small, swift hunters of the Triassic began to experiment with size and specialization in ways that would produce some of the most remarkable creatures ever to walk the earth. Consider Dilophosaurus, one of the early Jurassic predators whose fossils we find in the red sandstones of what is now Arizona. Standing nearly 10 feet tall and stretching 20 feet from nose to tail, it was already far larger than its Triassic ancestors. But it was also more sophisticated, with a distinctive double crest atop its skull and arms that, while still functional, were beginning to show the reduction that would characterize later theropods. Yet even Dilophosaurus was dwarfed by what was beginning to emerge in the herbivorous lineages. The early sauropods, creatures like Volcanodon and Baroposaurus, were experimenting with a body plan that would eventually produce the largest land animals in Earth's history. Their necks were growing longer, their bodies more massive, their digestive systems more complex. They were learning to process the vast quantities of plant matter necessary to fuel increasingly gigantic bodies. But perhaps most remarkably, they were learning to live together in ways that their ancestors never had. Fossil evidence suggests that even these early giants moved in herds, their footprints preserved in what were once mudflats, showing the passage of dozens of individuals travelling together across the Jurassic landscape. Imagine the ground trembling beneath the synchronized steps of 20 or 30 animals, each weighing several tons, as they moved from feeding ground to feeding ground in search of the enormous quantities of vegetation they required. The forests themselves were becoming partners in this evolutionary dance. The trees were growing taller, reaching toward a sun that shone more brightly through the humid atmosphere. And the dinosaurs were growing with them, developing longer necks to reach ever higher into the canopy, their browsing pressure encouraging the trees to grow even taller in response. It was an arms race of sorts, but one where both participants benefited. In the undergrowth, smaller dinosaurs were carving out their own niches. The ornithopods, ancestors of the duck-billed dinosaurs, were perfecting their ability to process tough, fibrous plants. Their jaws became more complex, developing batteries of teeth that could slice and grind vegetation with remarkable efficiency. Some, like the early stegosaurs, were experimenting with defensive armor, growing plates and spikes that would protect them from the predators that stalked the forest shadows. The Jurassic landscape was defined by water in a way that our modern world can barely comprehend. Rivers weren't just features in the landscape, they were the landscape, massive systems that drained continental watersheds and created environments of almost unimaginable richness. These weren't the relatively modest waterways we know today, constrained by human development and modern climate patterns. These were rivers that could stretch for thousands of miles, meandering across vast floodplains, where they deposited layers of sediment that would eventually become some of our richest fossil beds. The Morrison Formation in the American West preserves one such river system, and walking through its exposed rocks today is like reading the diary of a Jurassic world. Here, preserved in stone, are the footprints of sauropods as they waded through shallow waters, the mud squishing up between their massive toes. There are the remains of log jams, where entire forests were swept downstream during seasonal floods, creating tangled masses of wood that became temporary islands for smaller dinosaurs to shelter on. And everywhere there is evidence of abundance. The fossil record from these river systems is so rich that new species are still being discovered regularly, each one adding another piece to our understanding of how complex and diverse Jurassic ecosystems really were. These rivers supported not just dinosaurs, but entire food webs that stretched from microscopic plankton to massive marine crocodiles that could grow 40 feet long. Imagine standing on the bank of one of these Jurassic rivers as the day begins. The air is warm and humid, thick with the scent of vegetation and the earthy smell of rich mud. In the shallows, a herd of Camarasaurus has gathered to drink, their long necks stretching down to the water's surface, while their young shelter beneath their massive bodies. Their calls, low and resonant, carry across the water like the songs of whales. Farther upstream, a group of Stegosaurus picks their way carefully along the bank, their spiked tails held high as they search for the tender ferns that grow in the river's spray zone. The plates along their backs catch the morning light, perhaps flushing with colour as their blood vessels dilate in the warming air. They move with surprising grace for creatures so heavily armoured, each step carefully placed on the slippery mud. But the rivers were dangerous places too. In the deeper channels, predators waited. Crocodilians that had grown to enormous size in this abundant world lurked just beneath the surface, their eyes and nostrils barely breaking the water as they watched the herbivores drink. Some of these ancient crocodiles were built like modern forms, low and broad, perfectly adapted for ambush hunting in shallow water. Others had evolved more unusual body plans, with longer legs and more upright postures that allowed them to pursue prey on land as well as in water. And then there were the fish. The Jurassic rivers teemed with fish of all sizes, from tiny forms that fed on plankton to massive predators that could rival sharks in their ferocity. Some had evolved crushing teeth for dealing with the hard shells of freshwater mollusks. Others were sleek pursuit predators that hunted in the open water. The diversity was staggering, a reminder that the abundance we see in dinosaur fossils was matched by richness at every level of the ecosystem. The seasonal rhythms of these river systems helped drive the evolution of the creatures that depended on them. During the wet season, the rivers would swell beyond their banks, creating vast seasonal lakes and wetlands. Dinosaur herds would gather at these temporary water sources, mixing species that might rarely encounter each other during the drier months. It was during these gatherings that much of the social behaviour we see evidence for in dinosaur fossils likely developed. Fossil trackways show us glimpses of these interactions. Here, the footprints of a large theropod follow those of a sauropod herd, the predator perhaps waiting for an opportunity to separate a young or weak individual from the group. There, the the tracks of multiple ornithopod species converge on what was once a river crossing, suggesting that different herbivorous dinosaurs might have travelled together for protection. But the rivers offered more than just water and food. They were highways, allowing dinosaurs to travel vast distances across the fragmenting continents. River valleys provided corridors of lush vegetation that extended far into what would, otherwise, have been drier uplands. Along these green highways, dinosaur populations could maintain genetic contact across enormous ranges, preventing the isolation that might have led to extinction. The deposits left by these ancient river systems also preserved some of our most complete dinosaur fossils. When animals died near the water, their bodies were often quickly buried by sediment during floods, protecting them from scavengers and decay. This is why sites like the Morrison Formation and the Tendaguru beds in Tanzania have yielded such spectacular specimens, complete skeletons that allow us to reconstruct not just what these animals looked like, but how they lived, moved, and interacted with their environment. In these river deposits, we find evidence of dinosaur behaviour that would be impossible to deduce from bones alone. Coprolites, fossilised dung, tell us about diet and digestion. Gastroliths, stomach stones, reveal how sauropods process their food. Skin impressions show us the texture and patterns of dinosaur hides. Even dinosaur eggs, preserved in riverside nesting colonies, give us glimpses into their reproductive behaviour and parental care. As the Jurassic period progressed, these river systems became increasingly complex and diverse. The continued fragmentation of Pangaea created new drainage patterns, new mountain ranges to feed the rivers with sediment and nutrients. The climate continued to warm and humidify, supporting ever more lush vegetation along the waterways, and the dinosaurs continued to grow, both in size and in the sophistication of their adaptations to this watery world. The stage was being set for the emergence of the true giants, the massive sauropods that would define our image of the Jurassic period. But their story is inseparable from the story of the rivers that nourished them, the vast aquatic highways that made their enormous size not just possible, but advantageous. As we move deeper into the Jurassic world, we must remember that the Age of Dinosaurs was also the age of water, when Earth's landscapes were shaped as much by flowing rivers as by the massive feet that walked beside them. The humid air carries us forward, deeper into this ancient Eden, where giants are learning to be truly giant, and where every sunrise reveals new wonders in a world that seems almost too rich, too abundant, too impossibly alive to be real. By the Middle Jurassic, something extraordinary was happening to the very structure of life on Earth. The sauropods, those long-necked titans that had begun their journey as modest plant eaters, were undergoing a transformation so profound that it challenged the basic laws of physics and biology. They were becoming architectural impossibilities, living skyscrapers that somehow managed to walk. Consider for a moment the engineering challenge they faced. A Brachiosaurus, standing with its head raised to its full height, was lifting its brain nearly 50 feet above its heart. Think about that in human terms. It would be like your heart trying to pump blood to your brain while you're standing on the roof of a 5-story building. The pressure required would burst the blood vessels of any ordinary creature. Yet somehow these giants found solutions that allowed them to not just survive, but to thrive in numbers that boggle the imagination. Their hearts became massive, 4-chambered engines capable of generating pressures that would make a fire truck's pump seem gentle by comparison. But pressure alone wasn't enough. They evolved specialized blood vessels with muscular walls that could contract and expand, helping to push blood upward against gravity's relentless pull. Some researchers suggest they may have had multiple hearts, auxiliary pumps positioned along their necks like relay stations, though this remains a beautiful speculation preserved in stone that cannot quite speak all its secrets. Their necks themselves were marvels of engineering that would make any architect weep with envy. Composed of up to 19 vertebrae, each one hollowed out with air sacs that reduced weight while maintaining strength. They were essentially living cranes operated by an intricate system of muscles and ligaments. The largest sauropods could sweep their heads through an arc covering several acres without moving their feet, allowing them to strip entire groves of cycads and conifers while expending minimal energy. But perhaps most remarkably, they were social creatures. The fossil evidence grows stronger each year that these giants lived in herds, travelled together, and may have cooperated in ways we're only beginning to understand. Trackways preserved in ancient mudflats show the synchronized passage of dozens of individuals, adults on the outside, juveniles protected in the center, moving together across landscapes that stretched beyond any horizon their small brains could comprehend. Imagine the sound they must have made. Recent studies of sauropod skull anatomy suggest they were capable of producing infrasonic calls, sounds too low for human ears to detect, but powerful enough to carry for miles through the humid Jurassic air. Picture a herd of diplodocus calling to each other across a river valley, their voices creating a bass note so deep it vibrated through the ground, itself felt rather than heard by every living thing for miles around. The forests were reshaping themselves around these giants. Trees grew taller, competing for sunlight in a world where herbivores could browse 50 feet above the ground. The sauropods, in turn, became unwitting gardeners, their browsing pressure ensuring that no single plant species could dominate the canopy. They created clearings simply by walking, their massive feet trampling undergrowth and creating sunny spaces where smaller plants could flourish, and where the giants fed, predators followed. The Jurassic saw the evolution of hunters. Like Allosaurus, massive carnivores with jaws powerful enough to crack bone and teeth designed for slicing through flesh. But even these formidable predators faced a challenge that would test every aspect of their hunting skills. How do you bring down prey that weighs 30 times as much as you do? The answer lay not in brute force but in patience and cooperation. Fossil evidence suggests that large theropods may have hunted in coordinated groups, using their intelligence and endurance to wear down prey that was individually invincible. Bite marks on sauropod bones tell stories of attacks that were as much wars of attrition as battles, predators inflicting wounds and then following their quarry for days or weeks until blood loss and infection finally brought the giants down. Yet for every predator, there were dozens of herbivores. The Jurassic world was fundamentally a world of plant eaters, creatures that had learned to extract energy from the abundant vegetation with ever-increasing efficiency. Alongside the sauropods, other herbivorous dinosaurs were experimenting with their own solutions to the challenge of processing tough fibrous plants. The stegosaurs developed their distinctive backplates and tail spikes, but new research suggests these served functions far beyond simple defense. The plates may have been covered with blood vessels that could flush with color, turning each stegosaur into a living billboard capable of communicating with its own kind across the dappled shadows of the forest floor. Their small heads housed a surprisingly complex battery of teeth, perfectly designed for processing the cycads and ferns that made up their diet. In the undergrowth, smaller ornithopods were perfecting the art of rapid reproduction and efficient food processing. These were the rabbits of the dinosaur world, though rabbits the size of deer, capable of explosive population growth whenever conditions were favorable. Their sophisticated jaw mechanisms allowed them to chew their food with a grinding motion no living reptile can match, extracting maximum nutrition from every mouthful of vegetation. While giants walked the land, the oceans were undergoing their own extraordinary transformation. The shallow seas that had formed as Pangaea fragmented were becoming nurseries for marine reptiles that would grow to sizes rivaling the largest dinosaurs. These were not the oceans we know today, with their deep abyssal plains and sparse life. These were warm, shallow, incredibly productive waters that teemed with life from surface to seafloor. The ichthyosaurs had perfected their dolphin-like body plan, becoming pursuit predators capable of diving to tremendous depths in search of the squid and fish that form the base of the marine food web. The largest species, like Temnodontosaurus, grew to lengths exceeding 50 feet, their massive eyes, some over a foot in diameter, adapted for hunting in the perpetual twilight of the deep ocean. But it was the plesiosaurs that truly captured the alien nature of Jurassic seas. With their four-paddle propulsion system, they moved through the water unlike anything that exists today. The long-necked elasmosaurs used stealth and surprise, their serpentine necks allowing them to strike at prey from seemingly impossible angles. Their short-necked cousins, the pliosaurs, were pursuit predators of terrifying capability, some growing skulls over 6 feet long and developing bite forces that exceeded those of any known predator, terrestrial or marine. These marine reptiles had solved the problem of life in water in ways that no mammal would ever match. They were egg layers that had evolved to give birth to live young, their babies born tail first to prevent drowning during delivery. Some species show evidence of extended parental care, with juveniles staying close to their mothers for months or even years, learning the complex hunting techniques needed to survive in the competitive Jurassic oceans. The seas themselves were different in fundamental ways. The warm climate meant that temperature gradients between surface and deep water were minimal, allowing nutrients to circulate freely and supporting productivity levels that have no modern equivalent. Coral reefs grew in polar regions. Tropical marine ecosystems extended far into what we now consider temperate latitudes. And everywhere, the water was thick with planktonic life that formed the foundation for food webs of staggering complexity. On land, the air itself was changing. The abundance of plant life was pumping oxygen into the atmosphere at unprecedented rates, while the warm, humid climate was creating weather patterns unlike anything in the modern world. Vast convection systems carried moisture thousands of miles inland, supporting forests in regions that today are deserts. The very composition of the atmosphere was different, richer in oxygen, thicker, more supportive of the enormous metabolic demands of giant creatures. This oxygen-rich environment may have been crucial to the evolution of gigantism. Modern birds, which share many physiological features with dinosaurs, have respiratory systems that are far more efficient than those of mammals. They possess air sacs that allow for a one-way flow of air through their lungs, extracting oxygen with remarkable efficiency. Dinosaurs likely had similar systems, allowing them to maintain the high metabolic rates necessary to support their enormous body sizes in ways that would be impossible for mammals. The forests themselves were becoming more complex and stratified. The canopy level was dominated by tall conifers and cycads, creating a green ceiling that filtered sunlight into a perpetual twilight below. Beneath this upper story, tree ferns and smaller conifers formed a middle layer, while the forest floor was carpeted with ferns, horsetails, and the fallen fronds of the giants above. Each layer supported its own community of animals, from tiny mammals and early birds in the canopy to massive sauropods browsing at every level. And then there were the sounds. The Jurassic world was far from silent. The deep, resonant calls of sauropods provided a bass note that carried for miles, while smaller dinosaurs contributed a chorus of chirps, hisses, and roars that would have been utterly alien to modern ears. The forests rustled constantly, with the movement of creatures large and small, and the air hummed with insects, whose buzzing wings created a natural symphony that rose and fell with the rhythms of day and night. But perhaps most remarkably, this was a world in constant, gentle motion. The breakup of Pangaea continued, creating new mountain ranges and rift valleys, new coastlines, and inland seas. Volcanic activity was widespread, but generally mild, contributing to the greenhouse atmosphere that supported such abundant life. The continents themselves were drifting apart at rates measurable in human lifetimes, slowly creating the geographical framework that would define the rest of the Mesozoic era. As the Middle Jurassic gave way to the Late Jurassic, this world of giants and abundance was approaching its peak. The largest sauropods were still evolving, pushing the boundaries of what was physically possible for land animals. The marine reptiles were diversifying into forms of almost alien beauty, and in the undergrowth, small feathered creatures were taking their first tentative flights, beginning the journey that would eventually lead to the birds that fill our skies today. But change was coming. The climate that had been so stable for millions of years was beginning to shift once again. New mountain ranges were rising as the continents pulled apart, creating rain shadows and altering weather patterns. The sea levels were starting to fall, draining the shallow inland seas that had supported so much marine diversity. And in the south, the first stirrings of what would become the South Atlantic Ocean were beginning to separate Africa from South America, creating new barriers to the movement of terrestrial animals. The golden age of the Jurassic was drawing toward its close, but not before it would give us some of the most spectacular fossils ever discovered, creatures so perfectly preserved that we can still see the texture of their skin, the patterns of their feathers, and even, in rare cases, traces of their last meals. These windows into the deep past reveal a world of almost overwhelming richness and complexity, a time when Earth truly belonged to the dinosaurs, and life had achieved a grandeur that would never quite be matched again. The stage was being set for the final act of the dinosaur age, the Cretaceous period, when innovation and diversity would reach new heights, even as the first shadows of the coming catastrophe began to gather on the horizon. As the Jurassic faded into deep time, Earth prepared for its final and perhaps most spectacular act in the Age of Dinosaurs. The Cretaceous period stretched ahead like an unimaginably long summer, spanning nearly 80 million years of planetary evolution. To put that in perspective, the entire existence of our human species could fit into just the final few minutes of Cretaceous time, a reminder of how vast these ancient chapters truly were. The world that emerged from the Jurassic transition was both familiar and utterly transformed. The breakup of Pangaea had accelerated, and now great seaways were beginning to slice through the hearts of continents. Where once vast land masses had stretched unbroken from pole to pole, fingers of warm, shallow ocean now probed inland, creating tropical waterways that would reshape the very nature of life on Earth. These new inland seas were unlike anything in our modern world. Imagine oceans that stretched across what is now the American Midwest, from the Gulf of Mexico nearly to the Arctic Circle. Picture similar seaways flooding across Europe, Asia and Africa, creating archipelagos of islands where once there had been solid ground. The climate grew even warmer than it had been during the lush Jurassic, so warm that palm trees and crocodiles thrived within the Arctic Circle, and ice was banished from the planet entirely. In this hothouse world, evolution began one of its most creative periods. The early Cretaceous saw the emergence of flowering plants, angiosperms, whose colourful blooms would transform landscapes that had been green and brown for hundreds of millions of years. These weren't the simple flowers we might imagine, but an explosion of botanical innovation that would reshape terrestrial ecosystems from the ground up. The first flowers were small, perhaps unremarkable to eyes accustomed to the towering conifers and cycads that had dominated earlier periods, but they possessed something revolutionary: the ability to form partnerships with animals in ways that had never existed before. Insects, which had spent the previous 100 million years chewing on leaves and hunting each other, suddenly found themselves with a new profession. They became pollinators, carrying genetic material between plants in exchange for sweet rewards of nectar and protein-rich pollen. This partnership between flowers and insects triggered what botanists now call the the Cretaceous terrestrial revolution, a cascade of evolutionary innovation that affected every level of terrestrial ecosystems. New insects evolved to exploit flowering plants. New flowering plants evolved to attract specific insects. And the dinosaurs, those ancient masters of the plant-eating arts, found themselves adapting to a world where the very nature of vegetation was changing beneath their feet. The arrival of flowering plants created opportunities that herbivorous dinosaurs were quick to exploit. The hadrosaurs, or duck-billed dinosaurs, emerged as perhaps the most successful large herbivores of the Cretaceous, developing dental batteries that contained hundreds of teeth arranged in sophisticated grinding surfaces. These weren't simple plant cutters like their ancestors, but precision instruments capable of processing the tough, fibrous stems and leaves of the new flowering plants with remarkable efficiency. Picture Parasaurolophus standing at the edge of a Cretaceous marsh, its distinctive hollow crest catching the morning light. That crest wasn't merely decorative, it was a sophisticated musical instrument, a resonating chamber that could produce haunting calls that carried across the wetlands for miles. Recent computer modelling of these crests suggests that different species, even different individuals, could produce distinct tonal signatures, perhaps allowing for complex long-distance communication in a world where dense vegetation often obscured sightlines. The ceratopsians, those great horned dinosaurs of the late Cretaceous, were conducting their own experiments with social signalling and defense. Triceratops, with its massive frill and 3 distinctive horns, was just one member of a diverse family that had evolved an astonishing variety of skull ornamentation. Some, like Styracosaurus, bristled with spikes that would have made them look like living medieval weapons. Others, like Cosmoceratops, carried frills so elaborate and ornamented that they seem almost baroque in their complexity. But these weren't merely defensive structures, though they certainly could serve that purpose when massive predators threatened. Recent studies suggest that ceratopsian frills were primarily display structures, billboards of bone that could flush with blood vessels to create spectacular visual displays. Imagine herds of these creatures during mating season, their frills blazing with colour patterns we can only speculate about, creating visual symphonies across the Cretaceous landscape. The ankylosaurs took a different approach to the challenges of Cretaceous life, becoming living fortresses encased in bony armour that would have deflected all but the most determined predators. Ankylosaurus itself was like a biological tank, low-slung and massively built, with a tail that ended in a bony club capable of shattering the leg bones of any predator foolish enough to approach from behind. Yet even these armoured giants show evidence of complex social behaviours, with some species possibly living in small family groups that move together across the landscape. And then there were the sauropods, still present but changing with their times. The Cretaceous giants like Argentinosaurus and Puertosaurus pushed the boundaries of terrestrial size to their absolute limits, some potentially reaching lengths of over 130 feet and weights that may have exceeded 100 tons. These were creatures so large that their very existence challenges our understanding of how biology and physics can coexist. Where giant herbivores flourished, giant predators followed, and the Cretaceous produced some of the most formidable hunters in Earth's history. Tyrannosaurus rex, that icon of prehistoric predation, was actually just one member of a diverse family of tyrannosaurs that had evolved to fill apex predator roles across the northern continents. But T-Rex was special even among its fearsome relatives, a creature that had perfected the art of being a living siege engine. Standing 13 feet tall at the hip and stretching 40 feet from nose to tail, T-Rex possessed a skull designed around one simple principle: generating maximum bite force. Its jaws could exert pressures exceeding 12,000 pounds per square inch, enough to crush the bones of its prey like twigs. Those famous tiny arms, so often mocked in popular culture, were actually incredibly powerful appendages capable of lifting over 400 pounds each, though their exact function remains one of paleontology's enduring mysteries. But T-Rex was far from the only apex predator of its time. In the southern continents, other giants stalked the Cretaceous landscape. Giganotosaurus, discover Carcharodontosaurus, found in Argentina, may have exceeded T-Rex in size, while North Africa possessed teeth like railroad spikes and jaws built for slicing rather than crushing. Each of these predators was adapted for its specific environment and prey species, demonstrating that there was no single solution to the challenge of being a Cretaceous apex predator. The smaller theropods were undergoing their own remarkable evolution. The dromaeosaurs, or raptor dinosaurs, were perfecting pack hunting strategies that combined intelligence, speed, and those famous sickle-shaped killing claws. Utahraptor, the largest of these predators, stood nearly 7 feet tall and possessed claws over a foot long, curved like scythes and sharp enough to slice through flesh and bone with surgical precision. Recent discoveries have revealed that many of these smaller theropods were feathered, not for flight but for display, thermoregulation, and perhaps even brooding behaviour. The famous fighting dinosaurs, fossil from Mongolia, preserves a velociraptor locked in mortal combat with a protoceratops, but it also shows us that the raptor was covered in primitive feathers, giving us a glimpse of these predators as they actually appeared in life, part reptile, part bird, wholly alien to our modern experience. While giants battled on the ground below, the Cretaceous skies were witnessing a revolution of their own. The pterosaurs, those flying reptiles that had shared the Mesozoic skies with dinosaurs since the Triassic, were reaching the peak of their evolutionary success. Quetzalcoatlus, with its wingspan approaching that of a small airplane, was quite possibly the largest flying creature ever to take to the air. Standing as tall as a giraffe when folded on the ground, it moved through the sky with an efficiency that modern aircraft engineers can only envy. But the pterosaurs were no longer alone in the air. The first true birds had evolved from small theropod dinosaurs during the Jurassic, and by the Cretaceous, they were beginning to diversify into forms that would be recognizable to modern eyes. These early birds still retained many reptilian characteristics: teeth in their jaws, clawed fingers on their wings, long bony tails, but they had mastered powered flight in ways that would eventually allow them to outlive their giant cousins. The coexistence of pterosaurs and birds in Cretaceous skies created aerial ecosystems of remarkable complexity. Different species specialized in different flight styles, different hunting techniques, different food sources. Some pterosaurs became specialized fish eaters, skimming the surfaces of the warm Cretaceous seas like living seaplanes. Others developed filter-feeding mechanisms similar to modern flamingos, straining tiny organisms from the shallow lagoons that dotted the continental interiors. The birds, meanwhile, were experimenting with ecological roles that pterosaurs had never explored. Some became diving specialists, plunging into the water from great heights to catch fish. Others developed the ability to perch and maneuver in dense vegetation, accessing food sources that were unavailable to their larger, more cumbersome flying reptile cousins. As the Cretaceous progressed, the partnership between flowering plants and their pollinators was creating feedback loops that drove evolution in unexpected directions. Plants began producing fruits, fleshy packages designed to entice animals to disperse their seeds. This innovation opened up entirely new ecological roles for dinosaurs and other animals, who became unwitting gardeners, spreading plant communities across the landscape through their digestive systems. The forests themselves were becoming more familiar to modern eyes, though still wonderfully alien in their details. Deciduous trees began to appear, their leaves changing colour with the seasons and creating the first autumn displays in Earth's history. These seasonal changes provided new rhythms for animal behaviour, new opportunities for creatures adapted to take advantage of the rich resources provided by falling leaves and seasonal fruits. In the understory, small mammals were beginning their own evolutionary expansion. No longer confined to the tiny shrew-like forms that had scurried in the shadows of dinosaur feet for over 100 million years, they were beginning to diversify into new ecological roles. Some grew to the size of modern raccoons or opossums, becoming the first relatively large mammals since the Triassic period. But perhaps most remarkably, some dinosaurs were beginning to develop behaviours that would seem almost mammalian to modern observers. Evidence suggests that some species engaged in complex parental care, with adults bringing food to their young long after hatching. Fossil nests show careful arrangement of eggs, and some specimens preserve adult dinosaurs apparently brooding their clutches like modern birds. The social behaviours of Cretaceous dinosaurs were becoming increasingly sophisticated. Maiasaura, the good mother lizard, built colonial nesting grounds where dozens of adults would raise their young together, creating what were essentially dinosaur cities. The young remained in the nests for weeks after hatching, growing rapidly on food brought by their parents, developing the strength and coordination they would need to survive in a world full of predators. While the land was dominated by dinosaurs, the Cretaceous oceans had become the realm of marine reptiles that had grown to truly monstrous proportions. The mosasaurs, marine lizards that had evolved from terrestrial ancestors, were becoming the apex predators of the shallow seas that flooded the continental interiors. Tylosaurus, stretching over 50 feet in length, was essentially a marine dragon, its powerful tail propelling it through the water at speeds that would have made it a terror to any creature unfortunate enough to cross its path. These weren't the only giants in Cretaceous seas. The plesiosaurs had continued their own evolutionary journey, with some species developing necks so long they seemed almost serpentine. Elasmosaurus possessed a neck containing 72 vertebrae, allowing it to strike at prey from seemingly impossible angles while keeping its massive body hidden in the depths. And so we come to the end of our journey through deep time, standing at the threshold of the great extinction that would close the age of dinosaurs forever. For 165 million years, these remarkable creatures had shaped the very character of our planet, transforming it from a barren world, recovering from catastrophe, into a living Eden of unimaginable abundance and diversity. We've walked beside the first tentative steps of early dinosaurs in the harsh Triassic desert, witnessed their rise to dominance as Pangaea cracked apart, and marvelled at the giants that filled the humid forests of the Jurassic. We've seen them adapt and innovate through the flowering revolution of the Cretaceous, creating partnerships with plants and perfecting social behaviours that would seem familiar to any modern observer. But perhaps the most profound lesson of their story is this: nothing in nature is permanent, yet everything is connected. The same forces that allowed dinosaurs to flourish for so long, volcanic activity, continental drift, changing climates, would eventually bring about their end. Yet their legacy lives on in ways both obvious and subtle, from the birds that sing outside your window to the very landscapes that surround us, all shaped by the deep rhythms of a planet that continues its ancient dance through space and time. As you drift off tonight, remember that you are part of this same story, a brief but meaningful chapter in Earth's ongoing experiment with consciousness and wonder. Sleep well, fellow traveller through time, knowing that the same forces that shaped the age of dinosaurs continue to shape our world today, writing new chapters in the endless book of deep time. If you're drawn to these kinds of journeys through Earth's hidden chapters, you might find yourself wondering, what if Earth had never split into continents? The story of how our modern world came to be, and what might have been if the ancient supercontinent had remained whole, waiting for you in the quiet spaces between dreams. Quiet spaces between dreams.